My name is Lukas. I'm a PhD student at the Autonomous Systems Lab under the supervision of Roland at ETH Zurich. And my research topics mainly concern multimodal fusion of different sensors, of complementary sensors, but in the context of mapping and localization. So today, I would like to give a bit of an overview of our multi-robot and multimodal mapping and localization framework, specifically in degraded and challenging environments. And by this, I would like to start to motivate a bit why multiple robots are particularly interesting for us, as we have the goal or the aim that we explore some unknown environment as fast as possible, while being at the same time as accurate as possible. So multiple robots generally help us then that we can cover more areas of this environment at the same time compared to a single robot. For example, in the video on the right, we will see two robots are going to explore this part of the facility, and there's one robot going to explore this part of the facility. And exploring more or covering more area of an environment also means for us that we can improve our mapping and localization quality, in a sense that we have more information of it, we can fuse more information together. We employ here a global optimization framework that jointly optimizes over all robots. And if we have more information, we can use more constraints. And also, most of the time, the robots have some sort of overlapping areas like this entrance here to the facility, or they meet, in the field, and then we can add respective loop closures. We can connect the post graphs together and just have an improvement to our mapping pipeline here. As I said, I work with multimodality, so we don't really restrict which sensors our robots have. Of course, it would be beneficial for us if every robot has the same sensor suite. It would be nice, but typically in practice, it's not really possible. We have many different robots, real robots, legged systems, drones, and also for drones, we have weight constraints, and we cannot really put every super expensive, super nice and heavy sensor on it. So our system here, our mapping framework, seamlessly can handle multimodal information in a sense that we can add constraints from a visual system, but we can also add constraints from a LiDAR-based system. And in the end, our robots already employ quite a bit of complexity. They have to do all this autonomous planning, they have to do the control part, running the perception drivers and so on. So we don't want to really put more complexity on these systems. Instead, we employ here a centralized approach, meaning here at the entrance, we have a powerful base station where we send all the maps from the robots and transfer them back in chunks. Here we then combine them and then globally optimize given the information that we have from all the robots. When I talk about degraded environments, or challenging environments, I typically refer to man-made or natural environments such as mines, tunnels, caves, or also subway stations, nuclear power plants, these kind of things. And in the robotics community, there are like two important, I would say, applications to this. One is inspection, the autonomous inspection of some facility, but also search and rescue, where it's time critical for us that we find something quick, like survivors in a collapsed building or something similar. Here, I listed a few key challenges that we most of the time have when we go field testing. The first one is quite obvious. We cannot expect that each tunnel system is nicely illuminated for us. So we have to equip our robots with an active illumination, also in a way that this is synced to the rest of our sensor system, such that these things don't interfere with each other. And when we employ or deploy drones, these mines are sometimes dry and very, very dusty. So when they take off and essentially when they fly around, they blow up a lot of dust, which in combination with an active illumination can be super bad for a perception system. We mostly deal with unstructured, sometimes structured environments. But the point here I want to make is we have a lot of degraded situations, like we have very long straight tunnels, which look super self-similar, or super wide open spaces where you can't see anything at all, essentially. And for our system, we have to be resilient against this and yeah, correct any drift. And finally, there are two more practical considerations, one of which is that we don't have connection to the robot all the time. So there has to be some sort of autonomy involved. From a mapping perspective, we need to buffer the maps that we send back to the base station and then synchronize, check which ones we already have sent, which ones we don't have sent. But also this connection is limited in terms of the bandwidth. So we need to check how much we can send, as much as possible, as little as necessary. And finally, we deploy these robots in very harsh conditions. So we have mud, we have obstacles lying around. So this can cause issues with the locomotion, which in the end can cause issues to the state estimation of the robot, which we also need to correct for. So when I talk about this system, I like to divide this in three separate parts. The first one being concerned with the robots. So they build these local maps, which are essentially postgraphs. And then these local maps are sent in chunks to our mapping server, our base station, where we combine them and globally optimize them. And then finally, given this globally consistent map, we can send back information to the robots, giving them information, for example, of the existence of other robots, such that they can react more intelligently. And for the rest of this talk, I would like to go through these three parts in that sequential order, starting now with the first one, the red one. So the robots that we deploy, we don't really restrict which sort of state estimation they do. Can be visual, can be LiDAR, can be a combination of both. Most of the time, this is tailored to the specific platform, such that we get most benefit out of it. And then we only take the relative odometry estimates from these robots and build a local map out of it. And that is taking the odometry plus all the raw sensor data, like camera streams, point clouds, IMU messages. And for example, for the camera streams, we would track features on them and, given the odometry, triangulate them to a visual map. And with the point clouds, we actually don't do anything on the robots because we want to save computation. We only associate them with their respective location in the postgraph using the timestamp. Then every 20 seconds, we would subdivide this postgraph and send this chunk to the base station, and the base station then takes care of the rest. Here's an example of what this looks like. On the bottom part, we can see these 20-second windows. We build a visual map here. On the top one, you can see the features being tracked on 3 camera images. We support an arbitrary amount of cameras. It's just, there's again a trade-off between computation and accuracy. There's also one more experimental work that I would like to show. We also allow in our system that we project the LiDAR scans onto 2D images and perform a visual tracking pipeline on this. This has the nice benefit that the maps that we build, or at least the tracking that we do, is omnidirectionally. So it's 360 degrees around the robot, which can be nice for example, loop closures. So at the base station side, now we get to this second part. We've received some maps. So there's essentially one, it's a multi-threaded application. There's one thread that deals only with processing the global map, and there are multiple threads for the incoming submaps. We can see this here in this video on the right, and now the robot actually stopped, but the bottom part will correspond to what the robot sends. And this top one, the top part here, this colored one, will represent what the base station then received. We can directly see that here it accumulates all the maps that it gets. And the point here is also that before we actually merge the maps or the submaps into the global map, we will run a set of commands on these submaps in an isolated fashion. So we first want to make the postgraphs very tight before we can actually put this in the global map. And what we do here is we first perform visual loop closure on the submaps. Then we now take the point clouds that we previously associated with the postgraph and then do a consecutive scan to scan or scan to submap ICP registration. And each successful registration will then be inserted to the postgraph as a standard 6DOF constraint. And in the end, we would optimize this a tiny bit, just for a few iterations, such as that just like the postgraph is a bit tighter than without optimizing. So there's one thread then which continuously checks if there's new information available that we can merge into the global map. And essentially, we also take care, or we make sure that each submap overlaps a tiny bit with the previous one, such that there's a unique connection where we can attach it into the global map. We just need to take care of a few things, whether we have new observations in these overlapping areas or not, and then merge them accordingly. And then now finally arriving at this global map part where we have now all the information from all the other robots. Here we have a similar set of commands that we do, but the difference here is that this is running continuously in an endless loop. So we continuously check, do we have new information that we merge into? Then we perform visual loop closure, but now we perform it between all the robots, like all different robot missions. And instead of doing a consecutive scan-to-scan ICP registration, we now employ here what we call a proximity-based registration scheme. So here we take the poses and then perform a proximity search around it, like what we look up the nearest poses, the other poses, and then perform ICP to those poses. In the end, we would again do a full global optimization of the whole map. The difference here is that we also do it jointly over all robot missions, and similar as before, it's only for a few iterations. It's super tiny with the intention that we can quickly restart this loop, check if we have new information in there, and reincorporate everything that we have like up to date. This is an example of what these proximity point cloud registrations look like. So we have two robots here. One is going in this direction, and the other one is going in somewhat in this direction. And all these green lines that you can see in between, these are registrations that we did between them by looking up the closest poses. And of course, this is a bit of a tunable thing. We can check how many poses do we want to consider in the nearest neighbor lookup, and how far they can be away from each other. So this is a more detailed view of what our postgraphs look like. We'll just quickly go over it. We have 3 robots here, 1, 2, and 3. It's a standard postgraph with visual landmarks, IMU constraints, poses, odometry constraints. The point here I would like to make is how we can connect them to each other. And that is one thing we just saw, that is by doing these ICP constraints between the poses. And the other way is by doing visual loop closure, where we merge the landmarks that are involved in that loop closure. So for example, one landmark can have multiple reprojection areas to different robots. Okay, so this is a bit of a longer video now showing 3 different robots, one wheeled one and 2 animals, exploring one unknown environment. And this is actually post-processed, so that's why you can't see the other robots in the camera streams, in case you're wondering. Nevertheless, I really like this video because it nicely shows over time how we improve our mapping quality. And our experiments here really showed that this was just because we had multiple robots in that scenario, because then we were able to close more loops, we got more information of that environment. During the field, the robots actually employ a mesh network, a mesh antenna on themselves, such that the robots in between can act as a bridge to the base station. We also have a directional antenna here at the entrance that points towards the tunnel system. The animals also can drop Wi-Fi nodes along the way. We call them breadcrumbs, such that we can ensure connection back to the base station. As this video is quite long, there's also the ground truth in the back. I don't want to watch this to the very end. I will just show you the result that we got here. And actually in this image, we also included another robot. So in white is the ground truth. In magenta, there's one wheeled robot. Then there's one animal here in cyan, and there's another animal here in yellow, and there's one MEV here in green. It's a DJI M100. But what I'd like to point out is that all these 4 robots, they live in the same map. They share the same global optimization. So from that being said, now we have a globally consistent map of the environment. For us, it's not a question, what can we do with that information? And now we come to this third part of the system, where we actually send back information to the robots. And the way we approach this is by creating a sparse graph of the global graph. So we don't include all these super complicated constraints that we saw earlier, but rather just poses and like relative positions between them. In this way, the robots have a sparse information about the whole environment that we know so far. And they can then look up, for example, what was the latest known position of some other robot. And then the planner can say, okay, please don't plan in this direction. There is already some other robot, or this has already been explored by some other robot. We go in a different way. The other point is that we want to check out here is making the estimation, the state estimation of the robot consistent with what we have at the base station. So for this particular example, we employed a modified version of LOAM, of a LiDAR-based odometry on the robot, which also builds a post graph, a very tiny one, a sparse one. And then we can make these two, like the global sparse graph and the one from the robot, consistent by comparing these two. So here on the left, you can see like the estimation of the base station, given all the global information. And in green, there's the estimation of the robot. And by just checking them where they differ, and then we add corresponding constraints to their post graph, we can fuse them together and make it more consistent. Because this allows us now that at the base station, if there's, for example, some operator saying, okay, this robot should go in this direction or should explore in this direction, we can make sure that the point that we click and the robot that it receives has the same sort of coordinate frame that it explores. And here are a few more images that where we employed this system in different tunnel systems, in different mines throughout of Switzerland. And with that, I actually, at the end of my talk, if you want to know some specific part, I know it was not a very detailed presentation, but it's a very complicated distributed system. I think it's better if we actually discuss the details that you are interested in, and I can give you hints. Of course, if you want to know more, you can also shoot me an email for that. But anyway, thanks for having me here. Thanks for having the opportunity. It was a pleasure.